Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello friends, this video is on the topic measurement of medium resistances using the ammeter voltmeter method. Medium resistances are those resistances which are having the values in the range from 1 ohm to 100 kilo ohms. So all those resistances which are between these two ranges, they are termed as the medium resistances. So here we will study the ammeter voltmeter method for the measurement of such medium resistances. So let us start with our topic. In theory, there are various methods for the measurement of medium resistances like ammeter voltmeter method, substitution method, Wheatstone bridge method and Carey-Foster slide wire bridge method. Here we are studying the ammeter voltmeter method, which is the most popular and simple method for the measurement of medium resistances. This method is very simple because the instruments which it is using for the measurement, they are easily available in the laboratory. Here we will use one ammeter which will give us the reading of the current and one voltmeter which will give us the reading of the voltage. So ammeter and voltmeter, they are easily available in the laboratories. So this ammeter voltmeter method, it is used for the measurement of resistances in the labs. So let us start this topic. So ammeter will give us the reading of the current and voltmeter will give us the reading of the voltage. Now resistance can be calculated using the Ohm's law, which gives us the value of resistance as V by I. So here resistance is equal to this resistance value is the measured value of the resistance. So we will denote it as Rm. So it will be equal to the voltmeter reading divided by the ammeter reading. So voltmeter is measuring the voltage and ammeter is measuring the current. So R is equals to V by I, which is the Ohm's law. Okay. So through this formula we can calculate the value of the resistance. Now there are two ways in which we can connect the ammeter and voltmeter across the unknown resistance. So let us see those two connections. So these are the two connections for the ammeter and the voltmeter. R is the unknown resistance. In the first connection, you can see that the ammeter is connected close to the unknown resistance, whereas in the second connection, voltmeter is connected close to the unknown resistance. Now in the first case, we have this current. Now this current is given to the ammeter. Okay. Now ammeter is going to measure the current I, and voltmeter it is going to measure the sum of the voltages across the ammeter and across the resistance. Now ammeter and voltmeter, they will have some internal resistance. Suppose for voltmeter we have the internal resistance as RV, and for ammeter we are having the internal resistance as RA. So voltage drop across the ammeter will be VA, and voltage drop across the resistance will be VR. Current will be same across the two, ammeter and the unknown resistance. So here the voltmeter will measure the voltage V, which is the sum of VA plus VR, and ammeter it is going to measure the current, which is the current I, which is same across the unknown resistance also. Here in this case, the voltmeter will measure the actual voltage, which is the same across the unknown resistance, but current I, here we are having the current I. Now this I will be equal to IV plus IR. That is the current across resistance and across the voltmeter. Here voltmeter will again have the internal resistance as RV. Okay. So voltmeter will give us the reading, which is the same reading as that of the voltage across the unknown resistance, but current will be IV plus IR. So here in both the cases, we are not getting the true value of the voltage and the current. It is due to the ammeter and due to the voltmeter also. So we will get the true value only in the case when the resistance of the ammeter is 0 and the resistance of the voltmeter is infinite. Then only we will get the true readings from the voltmeter and from the ammeter, and we will be able to measure the accurate or the correct value of the unknown resistance. So here we will have a condition for this method, or there is a limitation of this method, that true value of resistance can be measured only if ammeter resistance is 0 and voltmeter resistance is infinite. So for this, RA, that is ammeter of resistance of the ammeter should be 0 and resistance of voltmeter should be infinite. But these conditions, that is RA equals to 0 and RV equals to infinite, these are the ideal conditions. Practically it is not possible. So this method, it will give us the inaccurate results, because ammeter and voltmeter in this case, they are not in their ideal state. They will have some internal resistance values also. So we will study the two connections, that how we can measure the resistance using these two connections of the ammeter and voltmeter. First we will consider the circuit number 1. Now in the first circuit, the ammeter is connected close to the resistance. So ammeter is measuring the true value of the current. Voltmeter is measuring the sum of the voltages. So in this case, voltage drop across ammeter, that is VA, is equals to RA. Okay, and voltage drop across resistance. V equals to IR. VR equals to IR. Now the voltmeter reading, resistance what we are measuring, suppose we are defining it as RM1. So RM1 will be voltmeter reading, that is V upon the ammeter reading. Voltmeter will read the sum of these voltages, so VA plus VR. And ammeter, it will give us the true value of the current. Now substituting the value of VA and VR, we will get IRA plus IR divided by R. So RM1 is equal to, if we take I as common, then I and I will be cancelled out. We will get RA plus R. So this is the measured value of the resistance which we are getting when we are using the circuit number 1. Now R was the true value of the resistance and RM1 is the measured value. So you can see that the measured value is higher than the true value of the resistance. Here the resistance of the ammeter is also adding up in this value. So we can say that measured value of resistance is greater than the true value of the resistance. So if we find out the difference, or if we find out the true value from this, so R will be equals to measured value minus the ammeter resistance. So R is equals to RM1 minus the RA. Okay. Now taking RM1 common, we will get 1 minus RA upon RM1. So from this formula we can say that the true value of the resistance will be equal to the measured value only if this ammeter resistance is 0. Okay, if it is 0, then this term can be neglected and R is equals to RM1. But practically it is not possible. The ammeter will have some internal resistance, so there will be some difference between the measured value and the true value, and this difference is called the error in the measurement. So we can calculate the error in the measurement by measuring the difference. Error will be equals to the difference between the measured value, that is RM1, minus the true value. Now if we are measuring the relative error, then relative error is equal to this absolute error divided by the true value of the resistance. So RM1 minus R divided by the true value, which is R. So this is the relative error. Now here if we substitute the value of RM1, which is what? R plus RA. So R plus RA minus this R upon R. So R and R, they are cancelled out. So relative error in the measurement is equals to RA by R. Now if we want to reduce this relative error, then we have to reduce the ammeter resistance. So if the ammeter resistance is very small and the resistance which we are measuring, it is very high as compared to this ammeter resistance, then the relative error will be small in the measurement. So we can say that error in the measurement is small. RA is small, or we can say that this resistance under measurement is very high because it is inversely proportional. Okay, so we can say that, or we can conclude that this method, this circuit number 1, where we are connecting the ammeter and voltmeter, ammeter is connected close to the unknown resistance, this circuit can be used for the measurement of high resistances, because if the resistance is high, then only the error in the measurement will be small. So this circuit is used So this was the first connection of the ammeter and the voltmeter. Now considering the second circuit, okay, that is circuit number 2. In the circuit number 2, we are connecting the voltmeter close to the resistance, unknown resistance. So voltmeter will give us the true value of the voltage, but ammeter, it is going to give us a reading which is the sum of the current across the voltmeter and the unknown resistance. So in this case, voltmeter reading will be V, but ammeter reading that is I will be equals to IR plus IV. Okay. Now IR is the current across the resistance. So using the Ohm's law, we can calculate the value of R. It will be equals to voltage divided by the resistance. So IR is equals to VR, that is the voltage across the resistance, which is equal to V only. Okay, and divided by the resistance. Now here we have IV, so IV is equal to the voltage drop across the voltmeter, which is equal to V only, and V divided by the voltmeter resistance, which is RV. So putting the value of IR and IV in this equation, we will get I equals to V by R plus V by RV. So this is the ammeter reading what we are getting, which is the sum of the current across the resistance and across the voltmeter. Now if we want to calculate the resistance, so the measured value of resistance will be equal to the voltmeter reading divided by the ammeter reading. So measured value of resistance So here if we denote the measured value by RM2, then RM2 will be equal to the voltmeter reading, that is V divided by the ammeter reading, that is I. So RM2 is equal to V upon I is what? The sum of the currents, that is IR plus IV. So substituting the value here, V by R plus V by RV. So if we take V as common, so V and V will be cancelled. So RM2 is equal to R upon 1 plus R by RV. Okay, what we are doing, we have taken the LCM, and then we have this V is taken as common, this will be cancelled, and after that we have taken the LCM. So we are getting the value of the resistance as this. Now from this formula, if we get the true value of the resistance, true value is what? R. So through this formula, if we get the value of this resistance, it will be Rm2 into Rv upon Rv minus Rn2. Or we can say R is equals to, if we take Rm2 as common, so this is the true value of the resistance. Now if you see this formula, what we are getting, the measured value is smaller than the true value of the resistance, because we are dividing the true value with this ratio. So measured value will be smaller than the true value. If we want that the measured value will become equal to the true value, then what we have to do, we have to make this ratio as 0. So this ratio will be 0 when the resistance of the voltmeter is infinite. When this is infinite, this ratio will become 0. So 1 upon 1 minus 0, this term will be neglected. So the true value will be equal to the measured value. So to make these two values equal, it should be that the resistance of the voltmeter should be infinite. But this is an ideal condition. Practically, it is not possible that the voltmeter resistance is infinite. It will have some value of the internal resistance, that is Rv. So the measured value will always be smaller than the true value of the resistance. So in this case, we can measure the error, which is the difference between the measured value and the true value. Suppose measured value is what we calculate is Rm2 minus the true value. Okay. So Rm2 we have already calculated, just putting the value of this measured value here. Now if we want to calculate the relative error, so relative error will be Rm2 minus R divided by the true value, that is absolute error divided by the true value. Now here if we put the value of Rm2, then we can calculate the relative error as minus of R upon Rv. So absolute error in this case, this relative error, if we represent it by epsilon r, then it will be equal to minus r by Rv. So if we want that this relative error is small, then what we have to do, we have to make this voltmeter resistance as infinite. When the value of this voltmeter is very large, then error will be small. Also, if the resistance what we are measuring, it is very small as compared to this voltmeter resistance, then also the error will be small. So we can make a conclusion that this error will be small when the resistance under measurement is small as compared to the voltmeter resistance. Okay, so this circuit will be used only when we are measuring low resistances. So when the resistance measuring, what we are measuring is small, then error will be small and we can get an accurate value of the unknown resistance. So this circuit is used. So first circuit we were using when we are measuring the high resistances. We are using the second circuit when low resistances are to be measured. So the two connections which we saw for the voltmeter and the ammeter, these two connections, the first circuit we are using for the high resistances and second circuit we are using for the low resistances. Okay, now what is the division point between the two circuits? For what values we will use the first circuit and for what values we are going to use the second circuit. So to get the division point, what we will do, we will equate the relative errors of the two circuits. Okay, so when the two relative errors obtained from the two methods, they are equal, that will be the division point. Okay, so from first method we are getting the relative error as RA by R, and from second method we are getting the value of relative error as R by RV. We are taking only the absolute values, so positive and negative signs they are neglected. Only their absolute magnitude we are taking. So if we cross multiply it, we will get the value of R as R square is equals to RA RV. So R will be equals to under root of RA and RV. So if we have the value of the internal resistance of ammeter and the voltmeter, we are going to multiply it, then we will get its under root and calculate the value of the resistance. So all those values which are greater than this value, for that we will use the first method, and the values of the resistances less than this value we will use the second method. Suppose from this we are getting the value of the resistance as 10 ohm. So resistances greater than 10 ohm, we are going to use the first method for their measurement. And if we want to measure a resistance having value less than 10 ohm, so we will use the second method. Okay. So this is how we are going to decide that out of the two connections, which connection has to be used for the measurement of the resistance. Now if we talk about the advantages or the limitations and disadvantages of this method, then limitation is that we are getting an error, we cannot get an accurate results because due to the presence of the internal resistances of the ammeter and voltmeter, we will not be able to measure the true value. We will always get an error in the measurement. This is the limitation, because practically we are not using the ideal ammeter and voltmeter in the laboratories. Now talking about its advantage, it is a very simple method because ammeter and voltmeter, they are easily available, and the connections involved in this method, they are also very simple. Disadvantage is that we are getting an inaccurate result, that is a disadvantage. So these are the this is the ammeter and voltmeter method which is used for the measurement of medium resistances. So I hope that this topic is clear to you. Thank you.